Hello everyone. So today we are going to look into the case where you have the harmonic motion with friction, and on top of that we are going to have a forcing function. So now let us look at the case where you have a spring, and there is an object which is attached to the spring over here. And in this case, we will consider that the spring is initially in the equilibrium condition, right? So it means it is here very nicely. We have the y. We assume that the y here is equals to 0, and the lower one, the lower portion is positive y, and the upper part of the equilibrium line is going to be negative. And so here we have y equals to 0, and the velocity is equal to 0, which means that the object is at rest. And then you have a force which acts onto this object, making it vibrate, right? So it will have a harmonic motion because of this force. So now we want to consider the equation. We want to see how to solve the second order linear differential equation with friction and forcing function. Right, so what we do is now we have this equation which we all know, right? So we have this equation, and we can actually write it so that we have this kind of equation where B is equals to L over 2m and C squared is equals to K over m. So C sometimes people write it as omega, but here we just want to be consistent. We use B and we use C over here. And then depends on this B and C, we will have three different conditions where you have the under dam, or you have a critically dam or over dam situation, right? So here we are just considering an under dam case. So we know the solution for under dam case, right? So how do we solve this? Is there is two steps process that we can use to solve this equation. So first, we assume that the f is equals to 0. Okay, so you will have a solution where f is equals to 0, and we call this as a homogeneous solution. So in the case where f is equals to 0, you know the solution for this case, which is written like this. Okay, you have the oscillating part. This one is the one that causes it to oscillate. But because of the friction, you have a damping. So you have exponential minus Vt over here. Okay, so V is related to this one, and this capital A and capital B is they are coefficients that you need to determine based on the initial conditions. And of course, beta over here is defined like this: c squared minus d squared. Right, so we have a first solution, and now we will guess the second solution for this equation, right? So what we need to do is we have to kind of we have to be smart in guessing, and the guess depends on the kind of force that you are applying to the system, right? So in this case, if you assume the F to be a constant, then you will try with the y, the solution for this equation y equals to a constant as well. But if your f is going to be like an exponential term, then you will assume you will try y to be proportional to an exponential function, right? So in this case, f is constant, so we will guess that y2 is going to be a constant. Okay, so we put this as d. Okay, and then I put a remark here since we consider a constant force F equals to 10, because we assume this is 10. So 10 Newton. So we just for the discussion, we will say this is 10 Newton. And then what we do is we will use this equation, the same equation, y2 equals to d, and we will put back into this equation over here, this whole thing here. So you are going to put y2 equals to d over here, d. But we know that this is constant, and therefore the derivative with respect to time is going to be equals to 0. So here you have 0, 0, c squared. Here y2 you have a d equals to f, right? So in this case your f is equals to 10, and from there you will determine what is your coefficient d, right? So now we have two solutions, one corresponding to a homogeneous equation, and one more which corresponds to a solution where you include the f, and now the total solution to the equation is going to be a combination of both. So you're going to take y equals to y1 plus y2. So you have this is the y1, the oscillating plus multiplied with the damping part, and then you have this forcing function, right? So now this is the general solution that we have, and the only thing left to do is to basically determine what is A and B according to our initial conditions. So now we will apply the initial condition in order to find our coefficients A and B. So the first initial condition is that the object is at the equilibrium at the starting point. So what we do is we will put y is equals to 0, put t equals to 0 in the equation, and you will get a plus b plus 10 over c squared equals to 0. So this will be the first equation. Then the second equation is that the velocity is equals to 0. So in order to find the velocity, you just have to differentiate the y with respect to t, and you will get this expression over here, this expression, and then what v is equals to 0, the velocity is equals to 0, therefore 0 at time t equals to 0, and then you have this expression here. Right, so now you have the second equation. So you have first equation, you have the second equation, and you can solve this by eliminating one of the coefficients, and then you find what is b, for example, and then you find, after you know b, then you use it to find a. So this is very straightforward because, for example, a plus b, you have a plus b equals to minus 10 over c squared, so you just have to replace this, and then you replace a, for example, into this equation, and then you can find what is b. So I will leave the derivation to you for you to do. And what I got is b is equals to 5b over c squared in bracket 1 over I beta minus 1. So once I have b, I just have to replace it into this equation, which I got from here, and then I will get my a. Right. So after we have done all this, and then we just have to simply put in b into the initial equation, the equation where you have this expression with the t non-zero. So you have to put b into this, a into this. You know as beta because beta is equals to c squared minus b squared, c squared minus b squared, and that's it. So then you will be able to describe the motion of the object. We will see the plots of this motion in the next slide very shortly. So now let us try to plot this harmonic motion with friction in the case where you have the object initially at rest, and then you exert a force onto this object so that it vibrates, undergoing a harmonic motion around the equilibrium point. So in order to solve this equation, we must input some values, right? So one of them, of course, we have to define the t. So in this case, I define my t from 0 to 10. And then you have 201 points in between so that we have a nicer curve later on. And then we have k, which is the spring constant, since we are considering spring case in this situation. So I just put k equals 2, L, which is the length of it. Just for the sake of simplicity, we put L equals to 0.1 and M is equals to 0.1. So here the first thing that we need to do before we actually do the plotting is to convince ourselves that these parameters will give you a case where you have a underdamp, right? So in order to define whether it is underdamp or not, you have to take a look at the beta value. So beta, if it is what we call that, imaginary number, then you have a harmonic motion. So in this case, beta, let me just put them. Beta is equals to square root of c squared minus b squared. I define this way because in the equation we have already imaginary number, the symbol I in front of the exponential term, right? So exponential I beta t. So in this case, the beta is a real number. But if you look at the initial expression, this is going to be b squared minus c squared, and you will see that this is an imaginary number. So beta, you have a b minus c squared. So b is from L over 2m, and c is equals to square root of k over m, right? So the difference between the two, so b is smaller than c squared, so you have an imaginary number, and therefore you have the oscillating part which is now in the category of underdamped motion. So let us revert back. Beta equals to c squared minus b squared, because this is the value that we are going to use in the plot. Right. So now we have convinced ourselves that this is the underdamped motion, and what we need to do now is to calculate. Next, we have to calculate what is beta. So beta, as we have seen from the previous slide, this is going to be 5b over c squared multiplied by parenthesis 1 over I beta minus 1. So then we have a, which is equals to minus b minus 10 over c squared. And now we can start to plot our motion, right, the harmonic motion. So what we do is we are going to plot t. Yeah, so before that I forgot to insert the y. So the y equals to exponential minus bt, then this is the oscillating part, plus this is the forcing function, right? So in this case, this is a constant force which is applied at the t equals to 0 at the starting point, right? So this constant force, how do we actually view it? You just imagine initially it is at rest, and then you kind of like provide some force to this object just for a little while, amounting to this value of 10 Newton, and then you don't disturb the system, and then the system is going to oscillate by itself, right? So now let's just enter, and we plot ty0. So this is the resulting plot that you have. So the x-axis here is to represent time, and here this is the motion of the object, right? Okay, so here you see that it will oscillate like this, right? So initially at time t is equals to 0, it is going upwards and downwards, and then it will slowly dies off. So this is underdamped motion, right? Okay, so let me just try to show to you now what you will get if you plot y as a function of x. That is, in this case, your x is static. So maybe we hope to see something meaningful from there. Right, so what I have here is a plot which is everything is on the straight line, because I'm plotting y as a function of x. So in this case, you have to remember that you have a motion of object on which is attached to a spring on a given straight line, right? So it's going to oscillate up and down like this. So initially you start with 0 over here, and then it will goes up and down. So you have so therefore you have something that looks in such a way. Okay, so I hope this is meaningful to you when you see it on the graph, and that is how you solve this harmonic motion with friction and the forcing function. So in this case, we have actually looked at the case where rather simplified in terms of mathematics, because you just have a constant force, but this is actually very physical, because you provide the force only at the beginning of the motion, and then you don't disturb it, and that is the graph that you have previously. So so in the case, if let's say, for example, you initially you provide a force at one time, and then you let it oscillate, and then you want to provide another force at another time, then you just have to kind of like take the superposition of two solutions, right, at this time where you actually exert the force on the system. Okay, so that's all from me. Hope it has been good for you. So thank you very much for your attention.